We are continuing with Rao Bhim 7.5. Today we shall discuss orthogonal projector. So just understand that this word is projector and not projection. Now we have already said what is meant by a projection. We have some subspace, call it S. This is the origin, and say we have a vector which is V. Now sunlight is shining perpendicularly on S. In that case, the shadow that this V casts on the screen, that is called the orthogonal projection of V onto S. Now it is quite easy to prove as well as intuitively see that if I have a parallelogram, then the shadow that will be cast on the screen will also be a parallelogram. So parallelograms cast parallelogram shadow, which means that this orthogonal projection is indeed a linear transformation. Now if it is a linear transformation, then we can find a matrix which will implement this. In other words, there must be a matrix which is called P. Of course, it will depend on S, such that PV will be the orthogonal projection of V onto column space, onto S. Such a matrix is called an orthogonal projector for S. Of course, I should call it the orthogonal projector for S, because given a space, orthogonal projection is a uniquely defined linear transformation, and hence it will have a unique matrix, assuming that you have already fixed a basis and all that. So we are interested in learning about properties of these orthogonal projectors. Before going into theorems, it will help if we take an example. Suppose we are working in R3, x-axis, y-axis and z-axis, and here is a vector V, which is suppose x, y, z, any arbitrary vector in R3, and I consider as my S, my screen, the xy plane, then the orthogonal projection of this is obviously given by x, y, 0. Now understand clearly that I am not saying that the orthogonal projection is x, y. The orthogonal projection resides in the same vector space as the original vector, so I have to write that 0 over here. So my linear transformation is the linear transformation which maps x, y, z to the vector x, y, 0. Now it is quite easy to see that the matrix which affects this is P equal to 1, 0, 0, 0, 1, 0, 0, 0, 0. If you do not immediately see it, just think of it as the identity matrix with this entry forcefully turned into 0. Because it's an identity matrix, so it will keep x, y, z unaltered, but since I have forcefully made this 0, this z is killed. So this is an example of an orthogonal projector. It is the orthogonal projector for the xy plane. First, let us discuss some very simple properties which are not explicitly written down in this particular section of the book. We have an inner product space V together with some subspace S of V, and let P be the orthogonal projector for S. So if I have any V in V, then this vector lying here will be PV. So you can clearly see that every vector of the form PV must lie in S. Now, every vector of the form PV is a typical element of column space of P. So immediately you see that column space of P must be inside S. But actually, since this orthogonal projection business is actually onto, so every vector in S can be considered as P times V. The simplest case is if I give you some vector, you just consider this as projection of itself, because the shadow cast by an object will be same as the object itself if the object is lying along the screen. So we see column space of P must be S. In fact, this has nothing to do with orthogonality. It is just a point about any projection. Now secondly, suppose I take something which is perpendicular, orthogonal to S. What will be the shadow cast by this? It will be just the point, which is just the zero thing. So if you are standing vertical and at 12 noon, in that case, your shadow is just a point at your feet. So I can say that if something is in S perp, in that case, that must also lie in null space of P. And obviously, if something lies in null space of P, then when you apply the projection P, it will become 0. So these two things must also be the same. And it's not very difficult to see that if a projection matrix, which we know is an idempotent matrix, satisfies these two conditions, it has to be an orthogonal projector. However, they are not very easy conditions to check. If you know that it is an orthogonal projector, there are interesting properties to use for solving other problems. But if someone gives you a matrix P and asks you to check if it is an orthogonal projector for some S without specifying S for you, then these conditions are not that easy to check. However, there is a much easier condition which is given by Theorem 7.5.12. Now this theorem, which I have recast slightly to make the presentation simpler, gives you three conditions and says that the following are equivalent. That is, if 1 holds, then 2 and 3 must hold. If 2 holds, 1 and 3 must hold. And if 3 holds, the other 2 must hold. Now I have stated this for real field. The book states them with stars here, P star, and works with, in general, with complex field. The proof remains exactly the same. Now, before we go into the proof, let's clearly understand that why it is useful. It's a very important thing, especially property 3. So it says P is an orthogonal projector onto some S. So this condition allows you to check whether a matrix is an orthogonal projector without having to first guess what that S is. So that is why this theorem is easier to use than the criteria that I gave you just now in terms of column space of P being S and null space of P being S perp. Now look at this condition, which is the most useful thing. It says P square must be equal to P, which is natural because every projection matrix is an idempotent matrix, and idempotent matrices are projection matrices. So these projection and these, they are basically one thing. Whatever you are stating in vectors and you are stating in terms of matrices. Now this condition of orthogonality translates nicely into this condition, which is symmetric. So a matrix is symmetric, idempotent, if and only if it is an orthogonal projector, and both these conditions are pretty easy to check. Now the second condition is also beautiful because unlike these two, which are two conditions, this is a single condition. And also when you prove it, it is easier to prove 1 to 2 or 2 to 3 instead of directly. But in practice, when you want to keep this in mind, remember 3, because this nicely splits up orthogonality into one condition and projector into another condition. Okay, so now let's start with the proof. Suppose I am showing that 1 implies 2. Now observe that if I have this situation, it is orthogonal projector onto something. So I have got a V and PV is a projection. What is left out here? What is that? It is V minus PV, which I can write as I minus P times V. Because PV plus this must together make a V, and these two things must be always orthogonal. And not only that, this I minus PV must be orthogonal not just to this vector but to every vector in column space of P, because column space of P is the screen. Because no one has specified an S, I know that the screen must be column space of P, which means if I take I minus PV, then it must be orthogonal to column space of P. Of course, this must hold for all V, and a typical element of column space of P is of the form P times U. So we basically need for all U and V, this thing must be perpendicular to any of these things. And since I am working with the real field, this means their inner product is 0 and the inner product is this transpose. I am working with just the usual inner product times I minus PV is equal to 0. And if I just expand it, this becomes U transpose, then I have got P transpose minus P transpose P, because this P has become P transpose, equal to 0. Now remember, this must hold for all U and V. So if I take U equal to say EI, those basis vectors 0, 0, 0 with only one at the point I, and similarly I take V equal to EJ, it is quite easy to see that this quantity will become just the ijth entry of this matrix. Now allowing U to vary over all Uys and allowing V to vary over all EJs, I can see that all its entries must be 0, which means that P prime minus P transpose P must be the 0 matrix. So I have shown that P transpose P is actually equal to P transpose. But hey, I was supposed to show that P transpose P is equal to P, but I have shown it is P transpose. That's not a problem. Just take one more transposition. In that case, we will see that P transpose will become P, and transpose of P transpose P is itself, it's a symmetric matrix. So when I take transpose of that, P transpose comes to the left, P transpose comes to the right. So you are back to P transpose P, and we have finished the proof of 1 implies 2. Now the reverse proof is already done here, because if this holds, then by taking transpose you can see that P transpose P must be P transpose, from which you can see this is 0. If this is 0, then for all UV this must be 0, and you retrace the steps, because all the steps are if and only, you get that I minus PV must be orthogonal to column space of P, which basically means that this thing is always perpendicular to that, and so it will be the orthogonal projector. So this argument is basically reversible, so it proves 1 and 2 are equivalent. The proof that 2 and 3 are equivalent, that is more like some algebraic thing. There's no trig in it, just direct put up everything. If P transpose P is P, then take transpose. We have already seen that since it is symmetric, P is a symmetric matrix, so you get this. So I am assuming 2, I get this easily. And if P is a symmetric matrix, then it is P, P times P is P, and that is this. So 2 implies 3. And if 3 holds, then it is very trivial to see that this must hold, because P transpose equal to P, so this is P square, so P square equal to P. I already have that P square equal to P, so I have proved it. So the equivalence between 2 and 3 is more like just rewriting a little bit. 1 and 2, that's where the linear algebraic argument comes in. But when you remember, I would never suggest that you waste your memory remembering this. Remember that 1 and 3 are equivalent, because this condition takes care of projector, this condition takes care of orthogonality. The next theorem will give us a way by which we can construct orthogonal projector onto a given subspace. We are of course working with finite dimensional vector spaces. So when I say you give me a subspace, I basically say that you give me some generating set for that subspace. So I will give you that construction. So here is your screen onto which we are trying to construct the orthogonal projector, and it is specified by a number of vectors that span the entire space. I am not saying that it has to be a basis. For example, here I have shown a 2-dimensional thing, but I have drawn 3 vectors. So they need not be all needed, but suppose for good measure you have got just a generating set. Now, based on these vectors, I want to actually construct an orthogonal projection matrix. Now you proceed in this way. You construct out of these vectors a matrix A. So this matrix A is made up of these vectors as the columns. So I have shown three things here. So these are the three columns. So S is column space of S, A. Now, when you try to construct the orthogonal projector, think of it in this way. I have some vector, possibly outside S, and I am trying to drop a perpendicular here, which means I am basically trying to do the following. This vector is, say, X, and I am trying to find a matrix P such that Px will be the foot of the perpendicular. So, in other words, the foot must be in column space of A. So, I am trying to look for X, and the foot of the perpendicular is something which is, say, A times some Y, that is the foot of the perpendicular, and I want this thing to be as close as possible. So, I will require that this cap, which is this thing, must be orthogonal to everything in S, that is, must be orthogonal to all the columns of A. So, this condition may be written as, you consider A y x minus a y, which is this fellow, and this must be perpendicular to all columns of A, which is A transpose this. If you are not clear, we used this argument just now. I am basically saying pick any vector here, it is of the form Az, and I am taking inner product of Az with this, which will give me Z prime this times this, and so since it has to be orthogonal to everything, so it must be for all Z. I can just take in place of Z the various basis vectors. So I will end up with saying that this must be 0, which basically says the first column of A, which is now lying down because I have taken transpose, times this vector is 0, inner product of this with the first thing is 0, similarly second thing and third thing, and so on. So anything that solves this equation will give me a required answer Y. So we have this equation just by rewriting, taking things on the other side. A transpose A y equal to A transpose X. Remember, X is given to you, and you are looking for, well, not really, you are not looking for Y, but you are looking for AY, that is the projection. And you want to express this AY as some matrix times X, and that some matrix will be your P. Now, the problem is this consistent? Well, a little bit of linear algebra should convince you that it is always consistent, but I would prefer that you look at this picture and see from these geometrically that it is bound to be consistent because there must be a foot of the perpendicular. But it is quite easy to see that it is all actually consistent because this is in column space of A transpose, and column space of A transpose is same as column space of A transpose A. That's a linear algebraic fact. So it is bound to be always consistent. So yeah, I want to take a solution of that. Now, if I have a consistent system, there is always a simple way of taking a solution. I can at least write down a solution in terms of G inverse. So suppose I take some G inverse and I take this. I am not saying how I construct the G inverse. Right now I said whatever G inverse you take, we know that for a consistent system this is going to be a solution. Okay, but remember, I am not interested in Y, I am interested in AY, the foot of the perpendicular. So P multiplying by A, I get this. And I have achieved what I wanted to achieve, namely expressing the foot of the perpendicular as some matrix times X, and this is true about for whatever X I take. So naturally, this fellow now serves the purpose of my P. And because I know that orthogonal projector has to be unique from its property, I can immediately conclude that whatever G inverse I take, somehow this must always remain the same. So this is invariant under choice of the G inverse. And that is precisely the statement of Theorem 7.5.13. However, they do not present it in that way. They will try to show that this is unique using some other earlier theorem, but I would never suggest that you try to remember it in that way. You first observe that P has to be unique. P is equal to this, hence it must be unique. That's a much smarter way of remembering it. Now, when I did this, I actually worked with any generating set. Now, in most practical situations, if you want to specify a subspace, you will not just take some generating set, you will take the basis, that is the minimal generating set. If you do that, in that case, A transpose A will be actually a non-singular matrix, and in that case, you can safely write inverse here, and that is the most commonly used situation.